All right, everyone, welcome to our third week of the graduate seminar for Math E15. Today we're finally going to prove some limits. The first week we focused on just understanding what a limit was and the different ways that a limit could exist or could fail to exist. And we decided then that what we really cared about was what happens as x gets near the point, not at all what happens as x equals whatever value x is approaching, only near the point. Last week, we introduced the real definition that took generations of mathematicians to come up with. I'll just remind ourselves of what that says. When we write the limit as x approaches c of f of x is L, and this is nothing new, this is just our definition from last time, means that no matter how small of an epsilon that person on the street chooses, he gives us some error bound up and down from L, we have to be able to find a delta, some difference in the x direction away from c, so that as long as the x's stay within delta units of c, remember that's what this is measuring, x minus c absolute value measures the distance that x is allowed to stray from c. So x can stray delta units in either direction. That will mean that the y values stray no more than epsilon up or down from what we think the limit L is. That's our definition from last week, and that's our picture of what's happening there. We think the limit is L. Whether this point L is there or absent doesn't matter, right? So for example, I could remove this point L, this point at x equals c, make one of those circles there, and make the value at x equals c somewhere higher. We don't care. The limit is still L because the limit is only about what happens near c. And near c, from both sides, we're approaching L in the y values. And we don't care at all about what happens at c. Any questions on the basic definition from last time? And we played around with that applet to try to understand. And what we usually found is that as epsilon got smaller, as the person on the street gave us a stricter and stricter, narrower window, then we had to make delta smaller as well in order to accommodate that person's demands, as it were. And then we did one example last week. We didn't do any proof. We're going to do the proof right away today. But for these limits, usually you do some scratch work, or I should say always you do some scratch work in advance of the proof. So we picked this boring function, f of x equals 4x minus 3 from last week, just a linear function and perfectly continuous, has no holes, nothing funny going on. And we were interested in what would happen as x goes to 2. And we saw that when x got near 2, the y values get closer and closer and closer to 5. So we think that this limit is, in fact, 5. And we're going to want to prove that today using this official definition. But before we do that, we do this scratch work sort of off on the side. That's not part of the proof, because that's what will enable us to write the proof, is having done this scratch work in advance. So how does it work? And again, this is all stuff we did last week. The person on the street gives us an epsilon. It's up to us to find a delta, so that when x is within delta units of 2, then the y values of the function will be within epsilon units of 5. Down here, the y values were allowed to go up to 5 plus epsilon and 5 minus epsilon. So then we work backwards. We're trying to prove our definition is a statement of the form if p, then q. Meaning in the proof, we'll start with the p statement and try to arrive at the q statement. But in the scratch work, we work backwards. We start with where we want to end up in the proof and work backwards. So we start with this part here. This is what we want to make happen. We want f of x minus 5 absolute value less than epsilon. So what did we do last week? We replaced f of x by its formula, 4x minus 3. And the natural thing to do seemed to be to combine the 3 and the 5 and get 8. And then people last week said, oh, well, we can factor out a 4 there. And we can, using this rule about absolute value that we talked about last week. And then the thing that we have control over, remember, is absolute x minus 2. We can control how far away from 2 we stray in the x direction. So look at that very nicely. What pops right out of our algebra here is absolute value of x minus 2. So if I move the 4 to the other side, we get absolute value of x minus 2 less than epsilon over 4. Meaning that if I replace this delta by epsilon over 4, then this statement will be able to walk its way back up to this statement, which is where we want to arrive. in the proof. So that was the scratch work we did last week. We decided that whatever epsilon the person on the street gave us, we would choose a delta to be a quarter of that. And that ends up hitting the corners perfectly in this graph, as in some of the examples that we saw last week. So the person on the street gives us an epsilon of 1. We choose delta to be a quarter, and it will work. Any questions on that so far? Yes?
Is delta always less than epsilon?
Delta is not always less than epsilon. So we'll see an example next week where delta will not be less than epsilon. But delta will virtually always depend on epsilon, unless your function f is a horizontal line, in which case, no matter what epsilon the person picks, you can choose any delta. As long as the function is somehow going up or going down, then the delta will always be a function of, will always depend on the epsilon. All right. Any other questions? So this is exciting. Now we're going to write our first proof. And the big difference between writing a proof in a math class and solving a problem in a math class is that in a problem, you might just write symbols and not write any words or any punctuation at all. But a proof should be written in nice, full sentences with capitalization and periods at the end and so forth to make it easy for the person who's reading the proof to understand. So that's how we're going to write our proofs here. And all of these proofs start the same way, pretty much. They all start with, suppose that the person on the street gives us an epsilon. So let epsilon greater than 0 be given. That's what happens. That person on the street chooses an epsilon. And now remember, the person who's reading this proof hasn't done any of this scratch work yet. So they don't know any of this stuff. So we're going to be nice to the person reading the proof, and we're going to give the person reading the proof a little roadmap of what we're going to do. Meaning we're going to write this stuff out again. So we must find what? The person on the street chooses an epsilon, and then we find the what? We find the delta. So we must find a delta greater than 0 such that, and then we're just going to fill in the blanks in our official formal epsilon delta definition. So if 0 is less than absolute x minus something is less than delta, and what's the something in this case?
C.
C, and what is the C for this particular function, this particular limit we're looking at?
C equals 2.
C equals 2. And just as a reminder, it won't be relevant in this problem, but in the next one it will. What does this 0 prevent x from equaling? If x minus 2 is strictly greater than 0, x can't equal 2, right? So in this case, it's no problem because there's nothing funny happening at 2. But in our next example, there will be, so we'll need to pay attention to that there. If that is true, then it's supposed to be f of x minus something is less than epsilon. And in this case, what are we putting there for our limit? We think the limit in this problem is 5. Now we're going to choose delta. And the only reason we know how to choose the delta is because we've already done all of this scratch work, right? So the person who's reading this proof is going to think, wow, these people are geniuses. How did they know to choose that delta? It's because we did the scratch work. So what are we going to choose for our delta? Epsilon divided by 4, right? That's because we did this scratch work. Now we're going to reap the benefit of that scratch work. So as we said, we're trying to prove a statement of the form if P, then Q. So you start with a part that you assume to be true, and then you work until you get to the part that you want to reach. Officially, and this is called the antecedent, and this is called the consequent if you're studying logic. So this is the statement we're going to start with. 0 is less than x minus 2 is less than delta. And now we need to go legally through with legal algebra, legal logic, until we get to f of x minus 5 is less than epsilon. Well, so this statement is just the same as saying 0 less than x minus 2 is less than what, given our choice of delta? Our choice of delta.
I'm sorry.
We chose delta to be epsilon over 4, right? Now, as we said, we don't need this 0 here, right, in this particular example. We never used the fact that x wasn't equal to 2 here in all of our scratch work. So we know that at the end, we're not going to need the 0 in this part. So at some point, we want to remove the 0, and we can do that right now and just say this is true. But you'll notice that we can't put a double-headed arrow here now, because there is an x value that makes this statement true that didn't make this one true, right? What could x not have equaled up here? 2. But now x can equal 2. But that's OK. We didn't have any trouble with x equaling 2 in our algebra here. All right. And now we're basically just going to follow our scratch work backwards, because we've done this scratch work over here. So we've got x minus 2 less than epsilon over 4. We run backwards. We bring the 4 to the left side. And now we can do the double-headed arrow, because those statements really are exactly the same. And would you agree that instead of writing 4, I could write absolute value of 4? Is that the same? 4 and absolute value of 4? They're the same, right? So now we're at this point in the scratch work. So what does the scratch work say to do next? Bring that 4 inside, right, using that same absolute value rule that we talked about last week. So then we get absolute value of 4x minus 8 is less than epsilon. And now here's the second occasion where we're really going to look like geniuses to the person reading the proof, because we're going to take this seemingly simple-looking thing, 4x minus 8, and we're going to actually make it look more complicated, because we want to go backwards from here. And instead of writing 4x minus 8, we'd rather write what? This top line. We'd rather break up the 8 into a 3 and a 5. So 4x minus 3 minus 5, all less than epsilon. And the only reason we knew to do that was because we had already gone through the trouble of doing the scratch work. So all of the real, whatever you want to call it, all of the real work is right here in the scratch work. The proof is essentially just running the scratch work backwards. Because now we're almost exactly where we want, right? We wanted to end up with f of x minus 5. Well, 4x minus 3 is our f of x. As desired, I think, is what I've written on the sheet. What do you sometimes write at the end of a proof?
Little square.
Sometimes you write a little square, so that's what the handout's got. So there's a little square. And the typesetting software that we use doesn't actually fill in the little square. Sometimes on a chalkboard, people will fill it in. So sometimes people will write that. Sometimes people will write what as well? There's some Latin, right?
QED.
QED. What does QED stand for? It's not an easy question. Quod erat demonstrandum which is Latin for that which was to be shown, that which was to be demonstrated. In other words, this is what we meant to demonstrate, this is what we meant to prove, this is what we meant to show. So this is a real proof that this limit is 5, because we have come up with a recipe that no matter what epsilon the person on the street gives us, we know how to choose the delta so that the graph stays where it's supposed to. Right? Well, there's nothing specific about this epsilon. Epsilon could be any positive number. Epsilon could be 1,000,000 if the guy on the street's in a really good mood. Epsilon could be 1/1,000,000 if the person on the street is in a really bad mood and wants to be tough with us. It doesn't matter. No matter what epsilon the person chooses, we choose our delta to be epsilon over 4, and this algebra will work. What do you think, our first proof? Yes, question?
I don't quite get the second line where you have the single arrow. And then
Right. So we knew that we wanted to end up with this without any 0 at the before it, right? That's what our definition tells us we need to end up with.
Okay.
You agree?
Yeah.
So at some point, we've got to drop the 0. Now, in many problems, the 0 will be important, because the 0 is what prevents x from equaling 2. In this case, the graph is continuous. So at x equals 2, the y value is 5. Nothing bad happens. We could have dropped it at any place along the way. We could have kept it all the way until here, in fact, and then dropped it. But I just chose to drop it at the start because I didn't want to write all those zeros all the way. So a one-sided arrow means that when the first statement is true, the second must also be true. That's what a one-sided arrow means. As opposed to a double-sided arrow, which means that if the first one is true, then the second is true, and if the second is true, then the first is true. Meaning a double-sided arrow means the two things are exactly equivalent. But here, because we dropped the 0, we technically should not be writing a double-sided arrow, because although whenever x satisfies this equation, x will be guaranteed to satisfy this equation, it's not true the other way around. Because what value of x satisfies this equation that didn't satisfy the first one is x equals 2.
Okay.
This is just a point in logic. So for example, we could say something like, I could have some statement like b equals 3 implies b squared equals 9. That statement is true, right? But is it also true to say that if b squared equals 9, then b has to be 3?
No.
No, because here b could also be what? Negative 3. So this statement is not true. So a one-sided arrow means that whenever the first one is true, the second one is also true.
Right.
But the second one could be true, right? In this case, b squared could be 9, even though b is not 3, right? B could be negative 3, and that would also make this statement true, right?
Right.
The example I always like to give when I teach the class on writing proofs that I teach during the day is about squares and rectangles. If you're a square, then you must be a rectangle, right? Square is the one where all the sides are the same.
Yeah.
But if you're a square, you're definitely a rectangle, right?
Yeah.
But is the other way true? If you're a rectangle, must you be a square?
No.
No. So that's the one that always helps me remember.
So when you put the 4 back, you multiply epsilon over 4 to get epsilon, and then you bring the 4 to the other side of the inequality.
Right. And multiplying each side of inequality by 4 doesn't change anything, right? So this is exactly the same statement as the previous one.
Then you have the double arrow again.
Right. Because these statements really are true. Like if you think about what the x's are that make this one true, they're the same as make this one true and make this one true and make this one true.
Oh, so the double arrow applies to the statement above it, not to the one.
Yes, yes, that's a good question. So the double-headed arrow, the way that we're doing it here, applies to the statement above it, not to this original statement. Very good question, right? I'm glad you brought that up. This statement is equivalent to this statement, but this statement is no longer equivalent to this statement, right? If we did have double-headed arrows all the way down, then any two statements along the way would have been equivalent. But this first statement is only equivalent to the second and none of the remaining ones.
Okay.
Great, good,
Thank you.
good. Should we try another example? So let's try one that's a little more complicated. So this is example 2. Now the function is f of x equals 2x squared minus 2 over x minus 1. We looked at this last week, and based on what we said last week, our claim was that the limit as x goes to, where is this function interesting? Where is the function interesting, though, at x equals 1? So the function is undefined at x equals 1, right? Because we'd be dividing by 0. But as x gets closer to 1, last week we decided, by looking at a table of values, that was our first example from last week, I think, we saw that the y values were getting closer and closer to 4, and then we confirmed this on that applet that we used last week. So we eventually want to prove this, but we're not going to be able to jump right into the proof. We have to do the scratch work first. So let's just remember what the scratch work says we're going to need to do. Given epsilon greater than 0, it's our job to find the delta such that and now we're just going to use our definition where we fill in the proper values for C and L. So the person on the street chooses an epsilon, and we find a delta, so that if 0 is less than x minus what in this case? 1, because that's our value of C, then f of x minus 4, because that's what we think our limit is. Okay. And then the scratch work starts the same way that it did in the previous problem. We're trying to prove a statement of if P, then Q. So we sort of cheat, and we start with the Q. We start with where we want to end up, because we're just doing the scratch work, so we can do whatever we want in the scratch work, as long as it's legal algebra. So we start with this statement where we want to end the proof, and we want to work backwards and somewhere find an x minus 1. So our function f of x, we can just replace it, 2x squared minus 2 over x minus 1 minus 4. Now with these problems where we have a rational function like this one and the next one as well, there's two paths you can take depending on your algebraic preferences. And both will lead you to the same delta in the end. So if you're choosing a different path, just make sure you end up with the same delta. So what are the two things that we could do to try to simplify things inside of that absolute values? So one thing is we can factor this numerator, right? And the other thing that we could do is we're taking a fraction minus a whole number, and if we wanted to do that, we could get a
Common denominator.
we could get a common denominator. So either one of those will work. So either you get a common denominator with this, or you factor the 2x squared minus 2. They'll both lead you to the same way. So let's do the factoring just for the heck of it. So if we factor this, we get what? We get 2 times x squared minus 1. And then I think as soon as you see x squared minus 1, you think about rewriting that as what? X plus 1 times x minus 1 all over x minus 1 minus 4. And now we would very much like to do what to simplify this? Cancel. And we're only allowed to cancel as long as we're sure, as you learned in your algebra class, you're not allowed to cancel when you're doing 0 over 0. How do we know that we're not canceling something of the form 0 over 0 here? We would only be doing that if x equaled what number? 1. And how do we know x is not going to be 1? We're looking as x approaches 1, meaning we don't care what happens at 1. Right? We only care what happens near 1. And this statement, when we do the proof, is going to prevent x from equaling what number? 1. Right? So we're allowed to do this next step, this canceling, only because we know x is not equal to 1. So I'll just write that. Since 0 is less than x minus 1, x is not equal to 1, meaning we did not do any danger of doing some illegal algebra by canceling 0 over 0. Is that OK? So this didn't matter in the first problem because the function was defined at the limit at the x at x equaled 2. But in this case, the function is not defined at x equals 1. And remember, what we're aiming for is to find an x minus 1 somewhere in here. Somewhere in here, we're looking to see an x minus 1. So what would you like to do to simplify this a little bit more now? If we multiply this out, we'll get what? 2x plus 2 minus 4, which will just give us 2x minus 2. And I hope you're liking that, because remember, we're aiming to find an x minus 1. Is there an x minus 1 hidden inside of 2x minus 2? If we factor out a 2, or absolute value of 2 if we're going to be absolutely careful. And there's the x minus 1 that we exactly want. Because x minus 1, remember, is what we have control over. That's how far away from 1 we're allowing x to move. So this is the same as just saying x minus 1 is less than epsilon over 2. Meaning, what should we choose for our delta? Epsilon over 2, right? Because we're going to start the proof by writing x minus 1 less than delta. And we know that if x minus 1 is less than epsilon over 2, then all of these statements lead back to here. So delta equals epsilon over 2 will work. Any questions on how the scratch work worked? Isn't it convenient how it's working out so nicely in both of these, that in the first one we found an x minus 2 and now we found an x minus 1? That's no coincidence. I mean, I've chosen these functions so that it does work out well. We'll see an example next week where it doesn't work out so perfectly. But for now, we're just concentrating on how the proof works. Let's write the proof. So all these proofs start the same. The person on the street gives us the what? Let epsilon greater than 0 be given. And again, remember that the person who's reading this proof has not done any of this scratch work, hasn't seen any of this scratch work. So we're going to be kind to the person reading the proof and, again, tell the person where we're going. So it's our job now to find the what? We have to find a delta. Delta has to be greater than 0, such that and what you'll find is that as you go farther and farther along in math classes, people tend to put fewer and fewer details in the proofs. But since we are just starting writing proofs, we're going to put in all the details everywhere. So we're going to find a delta such that if 0 is less than, simply what we wrote over here, x minus 1 less than delta, then f of x minus our limit of 4 will be less than that epsilon. Is that OK so far? So all these proofs pretty much start with the same first two sentences. Epsilon is given. We have to find a delta such that if this happens, then this other thing will happen. And now is our first chance to really shine in the eyes of the person reading the proof, because now we're going to choose, seemingly out of thin air, a delta. And what are we going to choose our delta to be?
Epsilon over 2.
Epsilon over 2, because we have gone to the trouble of doing this scratch work. Now we get rewarded for that. Then we're proving a statement of the form, again, if P, then Q. So in the proof, you start with the P part. So then 0 less than x minus 1 less than delta is equivalent to just saying 0 less than x minus 1 less than whatever we have chosen for delta, which in this case is what? Epsilon over 2, right? And now let's remember that in this case, the 0 matters, right? This 0 preventing x from equaling 1 is important to us because at some point in our scratch work, if you think backwards how we're going to go through the scratch work, we're going to go from this back to this, back to this, back to this. And when we get to this point, to move back to this step, we're going to multiply by 1 in a clever way, x minus 1 over x minus 1. But in order to do that with legal algebra, we have to be sure that we're not multiplying by 0 over 0, right? So we're going to have to keep this 0 less than that until we multiply by x minus 1 over x minus 1 to ensure that we are not multiplying by 0 over 0, which, as we know, is not legal algebra. So we're going to include the 0. So we're going to keep the double-headed arrows for a while here. So if we work backwards from the scratch work, the next thing is to move the 2 to the left side. And we can call the 2 absolute value of 2 if we feel like it. And when I multiply 2 by 0, I just get 0, right? So nothing changes on the 0 side there. And then if you look back to the scratch work, the next thing is to move the 2 inside of the absolute values using that same law of absolute values that we talked about last week. So now we can say 0 is less than 2x minus 2 is less than epsilon. And again, the only reason we know how to do these steps is because we've already done the scratch work. We get the proof for free once we've done the scratch work. And now is our second chance to really look smart to the person reading the proof, because we're going to take this seemingly simple 2x minus 2 and rewrite it in a more complicated way, 2 times quantity x plus 1 minus 4. And these statements are all exactly the same. All I'm doing is rearranging the terms in a way that is useful for us according to the scratch work. X. Oh, you mean now we want to multiply by x minus 1? Is that what you said?
No, like when we are taking 2 out.
So we in the scratch work, we went from this statement down to this statement, right, by simplifying? So now we're going to go backwards. So we can check. Like if I multiply this out, I get 2x plus 2, and then the minus 4, so that we do have the same thing that we had before. So that's good. And now we do again something that to the person reading the proof makes us look like geniuses. So we say we're going to make this even messier. We're going to multiply by x minus 1 over x minus 1. How'd you? Sorry. It's okay. And why were we allowed to multiply by this? We knew that we weren't multiplying by 0 because still x is not equal to what number? 0. We knew we were not multiplying by 0 since x cannot equal 1. We were not multiplying by 0 over 0. So in fact, this was where we removed the 0. So if we want, you could either stop writing it now, stop writing it there, or if you don't, if that makes you a little nervous, we can stop in the next line. But we needed that 0 all the way, right, until now. This 0 kept x from equaling 1. Same thing. X can't equal 1 here. X can't equal 1 here. X can't equal 1 here. Because these are all just different ways of writing an x minus 1 with a factor of 2, possibly. But this is great, because this thing in the absolute values now, isn't that pretty much exactly what we want? 2x squared minus 2, if I multiply out that numerator, minus 4, less than epsilon. because that's what we were aiming for, right? We were aiming to get f of x minus 4, and this is the formula for our f of x. So then that is just another way of writing f of x minus 4 less than epsilon as desired. And then we can put our little box to denote that the proof is done.
Excuse me, Professor.
Yes.
Did you cancel the x minus 1?
Yes, and the reason that we were, yes, right. Well, no, we didn't cancel it. We just multiplied out here. We just distributed the 2 times x plus 1, x minus 1 to get this. Because that was our function. The function that we're looking at is 2x squared minus 2 over x minus 1. So what do you think about that proof?
As long as you do the scratch work.
As long as you do the scratch work, it works, right? And one thing to realize is that, before we can even do any of these proofs, we have to know what the limit is. So this is very different than what you might have seen in other math classes where you're interested in finding the answer, and the answer is like a number or a graph or something. Here, finding the answer is just the start. Once we found that the limit was 4, now we're going to go ahead and prove it. So in some classes, if you're taking this class, for example, just for undergraduate credit, you're happy just to know what the limit is, and that's the point, to figure out how to solve the problem. But here, we're figuring out how to really prove that the limit is what we think it is, namely 4. So it's a much different focus that we're doing in this seminar. We're not interested in solving the problem, getting the answer. We're interested in proving that our answer is what we think it is.
Historically, this was done later than Newton's time.
This was done much later than Newton's time. Newton and Leibniz were long dead. But people before that were able to get all the right answers. You can get all the right answers without having a formal definition of the limit. No problem. So we have one more example, and I'd like you guys to try that on your own or check with somebody else. Those of you who are watching from home, this is example 3 from the handout. So what you would need to do there is first figure out what the limit L is. So maybe graph the function on your calculator or make a table of values by plugging in values for x very near 3. Do the scratch work, figure out what your delta should be, and then write the proof. So we'll stop the camera now, and we'll do that, and then we'll come back and check out the answer.